Hello, and welcome to a practice run-through of my qualifying exam. Today I'll be presenting a paper called Demystifying Reproducibility in Meta and Multitask RL, which has the shorter, pithier title, Details Matter in MTRL. First, I'd like to give a little bit of context around this paper, and then I'll get into the presentation proper. This paper came out of work that was done in late 2019, and then it was written in early 2020. We submitted it to ICML 2020 and also NeurIPS 2020, where it was rejected in both cases. But the results of this paper led directly to the development of a second version of MetaWorld, where we overhauled a large portion of MetaWorld's design and internals. And that really changed all the details in terms of the experimental results of this paper, but the key results from those experiments still basically hold up, and I'll get into later why I think that is the case. So before I get into really what we've done experimentally and what the purpose of this paper is, I need to describe a little bit about what reinforcement learning and in particular multitask and meta reinforcement learning are. So reinforcement learning, for the purpose of this talk, is using some reward signal to train a neural network to perform some task in an environment. In multitask reinforcement learning and meta reinforcement learning, we have some distribution of tasks that hopefully have some commonality to them that can be exploited. In multitask reinforcement learning, we try to learn all of those tasks jointly as efficiently as possible. In meta reinforcement learning, we have a slightly different objective, where we try to learn any one of those tasks quickly. And then there is some subset of that distribution that was held out as test tasks that we will then evaluate this learned learning ability on. In this paper, we treat these two quite similarly. Notably, you can use any meta RL algorithm as a multitask RL algorithm. And recently, a paper has shown that actually you can achieve meta RL learning by meta RL via doing multitask RL. So I think that the decision to treat these very similarly was appropriate. In this paper, we're really interested in a type of commonality that is still quite challenging to make use of, which is commonality between different kinematic tasks. So a simple type of commonality is parametric. A simple type of variation is parametric variation, where, say, you have multiple tasks to grab an object, and the object's location varies, and that determines what the task is the object's location. In this paper, we're mostly interested in tasks where they vary in non-parametric ways, which means that one task might be grabbing a puck, it could be at various locations, and another task might be opening a window, or another task might be closing a window, etc. But still using the same robot arm and hopefully having some commonality between the different tasks. Prior to about 2020, most research in meta RL in particular, and multitask RL when it was done, typically made use of other types of parametric variation. So here I've shown some of the main diagrams from the major meta RL papers in the field. You can see on the left essentially a goal inference, where you have to infer which direction in a semicircle to direct the agent. On the bottom left corner here is a curve fitting variation, where the scale and phase offset of the curves varies as the task. On the right here, we have two tasks that are related of moving around a simple kinematic agent. On the top, we have this ant, and on the bottom, we have a half cheetah, which you can see has one of two directions to move in. Arguably, this is non-parametric, but in a very simple way. In this paper, we make use of a benchmark called MetaWorld. That has these 50 tasks among them, and I don't expect you to really look in these tasks in detail, although there is a lot of interesting detail to find here. this demonstrates how these tasks have significant kinematic variation. It's also worth noting that this was a cross-institutional effort, and one of the original authors on this paper, Ryan Julian, also worked with me on a prior version of this manuscript. Those 50 tasks are then split up into multiple benchmarks, some of which are multitask benchmarks, meaning that they are just a set of the tasks, and some of them are meta RL benchmarks. So there's a set of training tasks and a set of test tasks, as indicated at the bottom here. And they come in approximately 3 different scales: ML1, that simply has parametric variation within a task; ML10, which has and MT10, which have 10 training tasks, and in the ML10 case, 5 test tasks; and the largest set that has all 50 tasks. In the multitask setting, all of them are together in one set. In the meta-learning setting, there's 45 training tasks and 5 test tasks. So that gives a sense of scale and notion of the kinematic variation we're working with here. The first big contribution of this paper is a library called Garage. It's the meta-RL library we've created, but the most important thing for this paper is it's the first library to contain all of the commonly used meta-RL and multitask RL algorithms in one place, and they're defined using common terms and are able to run on commodity hardware, which prior implementations of these algorithms could run on commodity hardware for small experiments, but not easily for, say, ML45. MAML would require half a terabyte of RAM to run an ML45, which is not practical for most research groups to use. The other reason that we really think Garage is important is that in single task RL, the difficulties around small details mattering in single task RL have been as much as possible addressed by having a common good implementation that everyone uses. And that ensures that if everyone uses that same set of baselines, then everyone's comparing against the same objectives, and this minimizes confusion about the performance of various algorithms. In this paper, we take an experimental methodology to show that not only do small details matter in single task RL, but they also matter significantly in meta and multitask RL. In total, we end up using about 500 runs, and the general procedure we use for performing one of these experiments is we have an implementation of an algorithm that we think is fairly well tuned. It's been reviewed when possible by the original authors, and we've run tests to make sure it performs well in other basic benchmarks. We call it the control implementation. Then we make a small change to it and run that small change multiple times on the same benchmark that we ran the control implementation on. Then we take each of those runs and we reduce it to a single performance figure, a single number. And then we take those 2 groups of runs, the control runs and the experiment runs, and we perform a t-test to determine whether or not our change made a difference. This comes out of a protocol that was recommended by other researchers, and it seems to work pretty well in that, even though the underlying benchmark has been changed significantly, the results I'm about to present, I believe, still hold. So what did we find? So first, we found some details that are really specific to meta-RL and could also be really big. So one thing that's specific to multitasking meta-RL is that in order to judge the performance of an algorithm across a set of tasks, instead of using reward scales and just adding the reward scales of adding the rewards of all the tasks together, which might give a misleading picture if some of the tasks have much higher reward scales, or simply doesn't describe whether or not you've succeeded across all tasks or a small set of them very well. Instead, we can use a binary success metric that says whether or not you've succeeded in a run or failed. And it turns out this reward scaling difficulty also matters a lot during training. So in proximal policy optimization and potentially other on-policy reinforcement learning, a common method to ensure that learning continues throughout the training process is to normalize the variance of the reward signal. So you take a rolling average of the reward and its variance, you divide out the variance, and then you get a reward signal that always has unit variance. So there's two slightly different ways you can apply this in multitask and MTRL learning. One is you can compute those statistics about the reward signal, the variance and the mean, per task, divide them out to get unit variance reward signal for each task, and then shuffle those data points together. Or you can first shuffle the data points together and then compute the variance, divide it out, and get unit variance across all tasks. It turns out that the first of those is much, much more effective than the latter for at least all the on-policy methods we tried. So RL squared PPO in this case improves in performance by over 100%. By first per task, by taking the reward signal of each task separately, making it have unit variance, and then shuffling those together. However, this type of naive reward normalization actually causes multitask soft actor critic to have significant issues, which I get into in more detail in the manuscript, but essentially this is just not appropriate for Q learning. But a similar approach could be made to work, perhaps. We also find that single task reinforcement learning details can still matter in some cases. So one issue that can happen in, especially applying Q learning, is that if you have a time limit to your environment, one way you could express that time limit is when the time limit is reached, the agent is forcibly transferred to a terminal state. So some MDPs contain terminal states, and having to reason about them correctly is a necessary part of Q learning. But if you do this, and that means there's this hidden variable, the time variable, that is not observed by the agent. And that makes it really impossible to fit a Q function accurately to the data. And this causes octocritic methods to usually perform very poorly. And we do find that this significantly hampers the performance of multitask soft actor critic. Notably, fixing this issue does not improve the performance of Perl, which essentially is doing a variational inference on top of multitask SAC in order to do meta learning, indicating that there's some other issues that Perl has on these benchmarks. Finally, I want to give an example of how small of detail can still have an impact. So RL squared is an algorithm that uses a rather clever trick to solve meta-RL. It treats reinforcement learning itself as a reinforcement learning problem, as the name suggests. And the way it does that is it trains a recursive neural recurrent neural network, in this case we use the GRU, to learn how to do reinforcement learning by feeding it multiple episodes at a time. In the early episodes, it figures out how to solve the task, and in the later episodes, it performs the task. In this setting, there's two slightly different options you have for how to compute the returns from the reward signal. So one option is you first, on the left, as described on the left here, and this is as described in the original paper, is you first take all of the episodes, you concatenate them together, and then you compute returns. So if in the second episode here, you've got the reward shown here, that implies that there's a return correction leading back into the past that includes this episode, but also the end of the prior episode. Now these two episodes are not causally connected except through the recurrent neural network, so it doesn't necessarily make sense to do this. And the most common implementation doesn't. It computes returns separately for every episode, and then takes that return signal and uses it to train the recurrent neural network. However, we find that it matters significantly. If you look at this performance plot, somewhere between 40% success here and maybe 70%, that's a very large difference in performance. And this is after 20 million time steps, or about 100,000 episodes. Thousands of hours of time training a robot if it's a real world robot. This might seem like a reasonable time to stop the experiment, but thankfully Garage can keep running this experiment. And if you do that, you see that eventually these curves do converge, but still this region in the middle here, if you only measure here, is statistically significant. And this holds across other benchmarks as well, as I mentioned in the manuscript. So that's just how small this change could be. And notably, this requires a different performance metric than we used in the other parts of the paper. There's not a statistically significant difference between the performance of the common implementation, which we marked pro and P here for the reasons I won't get into, and the performance that our implementation peaks at. And finally, I wanted to get into some of the results that really directly led to the design of MetaWorld v2. So, firstly, we were able to run all of the same algorithms that the MetaWorld paper ran, but instead of running them for 1 seed, we were able to run them for at least 9 seeds each. We aimed for 10, but running Perl on GPU is very challenging, but running Perl on CPU is very slow. So we settled in the end, because this paper is not becoming wasn't accepted at any conference. We've not had a strong reason to rerun it here, although actually this has been rerun for the MetaWorld v2 paper, which used our implementations. And you can see here that the best performing algorithm is multitask soft vector critic by a rather large margin, and all the other algorithms are solving a very small number of the tasks. On the test set, a single one of the tasks is solved, and this also holds for the smaller benchmark for the MT10 and ML10 benchmarks, where a small number, in this case about 2 of the tasks in the training set are solved, and almost one task is partially solved. And the final thing that really indicated that MetaWorld v1 needed issues to be used as an effective MetaRL benchmark, at least with the algorithms you have today, is that we were unable to get adaptation to happen as MetaRL is designed to have happen. So basically, we took here from each run of each of these algorithms the best model, and then we tried giving it various numbers of samples to adapt to the new task, ranging from just 64 samples up to I think 16,000 at the edge here. And nowhere in this range is there a significant evidence of adaptation. Fortunately, I believe that this has been largely resolved in MetaWorld v2, and we do see some amount of improvement there, although I don't have any graphs to show that. Thank you for coming. I will now take questions, except that this is going to be online, so I guess post the questions below, or email me. I should put my email.